thank you for the organization of this conference and this opportunity to speak. So I will speak about finite type invariants of null-homologous knots in rational homology spheres. So first I will introduce the object of this theory, so knots in rational homology spheres, and the moves that we will consider on these objects to define finite type invariants. Then I will make a brief recall of other series of finite type invariants that have been studied previously. And I will go on further on the subject by giving some description of the associated graded space of this theory, so which describes the graded space of finite type invariants for knots with an Alexander polynomial of degree at most 2. And I explain what are the difficulties to generalize this result. So first, our objects are what I call QSK pair, so SK for sphere knot, that are pairs MK, where M is a rational homology sphere, or Q sphere in short, and K is a knot in M, whose homology class in the first homology group of M with integral coefficients is trivial. On this object, we want to define a move called null-Lagrangian preserving surgery. So first, we need the notion of a rational homology under body. So a genus G rational homology under body, QHH in short, is a compact, connected, oriented three-manifold whose homology with rational coefficients is the same as the homology of the standard Handel body, which is drawn there. So the boundary of the Handel body is a compact, closed oriented surface of genus G, and it's quite easy to check that in general, for any rational homology under body, we also have that the boundary is homomorphic to this surface. And now we can define the Lagrangian of such a QHH. We consider the map between the H1 induced by the inclusion of the boundary of A in A, and the kernel of this map is called the Lagrangian of the QHH. So namely, the subspace generated the subspace of the H1 of the boundary, generated by the classes of closed curves that up to some multiple bound the surface inside the QHH. So once we have this notion, we can define the move of Lagrangian preserving surgery on a three-dimensional manifold. So in our case, we're interested in Q sphere. So we take a Q sphere M, a QHH A embedded in M, and another QHH B with the same genus as A, and we fix a homeomorphism between the boundaries which preserves the Lagrangian. And with this data, we can define the manifold obtained from M by the surgery B replaces A by removing the interior of A and gluing instead the QHH B along the homomorphism H. And thanks to this Lagrangian preserving condition, the obtained manifold is still a rational homology sphere. So this defines the move on rational homology spheres, and now we have to take into account our knot. So when we take a QSK pair NK, we will use a QHH embedded in the complement of the knot K, and we put this additional condition. So we have that A is null in M minus K, meaning that when we consider the map induced in homology by the inclusion of A in the complement of K, we want that this map has a trivial image. And then with the same data as before, we define the QSK pair obtained from MK by the surgery B replaces A by considering the manifold obtained by surgery and the copy of the knot K in the new manifold. So this defines the move of null-Lagrangian preserving surgery. So now we have our object, QSK pairs, our moves on these objects, null-Lagrangian preserving surgeries, and with this data we can define a theory of finite type invariants. So to do that, we will consider the rational vector space generated by all QSK pairs up to orientation preserving homomorphism. and we will define subspaces of this space F0. So we define the subspace Fn for a positive integer n as the subspace generated by all these brackets, where such a bracket is defined by a QSK pair, a family of n disjoint QHs in the complement of K, and another family of QHs with identification of the boundaries of the AI with the BI, where this identification has to preserve the Lagrangian. And the bracket is defined as the alternated sum of all the manifolds, all the QSK pairs obtained from MK by any subfamily of these M surgeries. So this gives a subspace of F0. It's easy to check that this defines a filtration of F0. And from that we have the notion of finite type invariant. So we'll consider here invariants with rational values. And a linear map from F0 to Q is a finite type invariant of degree at most n if it vanishes on the subspace Fn plus 1. And of course it's of degree exactly n if it is of degree at most n, but not of degree at most n minus 1. So this is a very general definition in the sense that if we are given any set of topological objects and any set of moves on these objects, we can make the same definition, replacing QSK pairs by our objects and replacing neural LP surgeries by our moves. So this is a very general setting. And when we have such a theory, we have an associated graded space, which is the direct sum of the quotients of the filtration. And so this graded space, its dual space is the space of finite type invariants graded by the degree. So when we study a theory of finite type invariants, one of the main goals is to give a description of this graded space G, a combinatorial description, in order to understand better the space of finite type invariants, and in order to be able to compare invariants and to measure their power. So in general, the idea is to construct some graded space of diagram, and together with a surjective map onto our graded space G. And to have a complete description, we need to have some universal invariant. Universal in the sense that it will realize the converse of this map. So, of course, constructing such an invariant is a big deal in theory. And one also has to describe precisely the behavior of this invariant with respect to the move which defines the theory, in order to prove that it defines a map on the graded space G. So, before going further into this theory, I would like to recall other series of finite type invariants that have been defined, have been studied. So the first one was defined by Gusarov and Vasilev, and dealt with knots in S3. With the move used in this theory was a change of crossing on the diagram of the knot. So for this theory, the graded space G have been described by Barnatin and Kontsevich using as a universal invariant the Kontsevich integral. By universal, of course, here we mean universal for finite type invariants. Of course, we don't know yet if Kontsevich integral is universal for not. So after that, different theories have been defined of finite type invariants for three-dimensional manifolds. The first one, historically speaking, is due to Otsuki and concern integral homology spheres. So other theory has been defined, and the one which will be important here in my talk is due to independently to Gusarov and Aviro, and it can be defined for any three-dimensional manifold, but it has been widely studied for integral homology spheres. So the move used in this theory is called Bourgogne surgery. I will recall in a few minutes what is the Bourgogne surgery. And the graded space in this case for integral homology spheres have been described by Garoufalidis, Moussard, and Polyak, using as a universal invariant the Murakami-Otsuki invariant defined by quantum methods from the Kontsevich integral of links. So 2 remarks on this theory. First, there is a result of Oakley and Lescop, which implies that you can define the same theory by using ZLP surgeries. So by ZLP, I mean Lagrangian preserving surgeries, as I have defined before, but considering always integral homology. So integral homology under bodies, integral Lagrangian, so on. So with these 2 moves, you get the same theory. And other remark, here, instead of the LMO invariant, one can also use the Kontsevich-Kopperberg-Thurston invariant, defined by integrals on configuration spaces. And so the fact that we can use it in this theory is due to formulas proved by Masuyo, who gives the behavior of this invariant with respect to Lagrangian preserving surgeries. And so this is an important result because it gives a way to compare these 2 invariants for integral homology spheres. These 2 invariants, both coming more or less from the idea of the Kontsevich integral, are very important invariants for homology spheres, but we do not know how to compare them directly. So the fact that they appear as universal invariants in this theory proves that they have the same power in separating integral homology spheres. I have a generalization of this theory in the case of fractional homology spheres. So with as object Q spheres as moved Lagrangian preserving surgeries, I describe the associated graded space. And once again, as a universal invariant, we have 2 possibilities. You can use either the LMO invariant or the KKT invariant, to which in both cases we have to add degree 1 invariants defined as the periodic variations of the cardinality of the first homology group. So once again, this provides a way to compare these 2 invariants in the case this time of rational homology spheres. Precisely what we can say is that if we take 2 rational homology spheres whose first homology group have the same cardinality, then they have the same LMO invariant up to some degree, if and only if they are the same KKT invariant up to the same degree. Okay, so now a theory concerning knots in homology sphere. So this theory is due to Garoufalidis and Kricker, and it's defined for any ZSK pairs. So ZSK pairs are knots in integral homology spheres, and the graded space have been described in the case of ZSK pairs with trivial Alexander polynomial. The move considered here is either null Borromean surgeries or null ZLP surgeries, so as before we have this choice. And the graded space for ZSK pairs with trivial Alexander polynomial has been described by Garoufalidis and Kricker using the Kricker invariant. So the Kricker invariant, which is some kind of equivariant version of the LMO invariant. And indeed, one can also use in this case the Lescop invariant, which is defined by integrals on configuration spaces. And so here we have again this possibility to give some equivalence between these 2 invariants for knots in integral homology spheres with trivial Alexander polynomial. So the goal of the work I will speak about in this talk so the study of finite type invariant for QSK pairs is to provide such an equivalence between the Kricker and the Lescop invariant for general QSK pairs. So back to QSK pairs. An important invariant here is the Alexander module with the Blanchfield form. So I briefly recall, when you take a QSK pair LK, you can consider the exterior of the knot. You remove the double neighborhood of the knot. and you have a natural map from the phi 1 to z, viewed as the first homology group of x up to torsion. And associated with the kernel of this map, you have the infinite cyclic covering of x. This infinite cyclic covering can be represented in this way. You have you take a ciphered surface of the node k. You have in x time the lift on this ciphered surface glued together by copies of n minus sigma. And the Alexander module of the pair is the first homology group. Here I consider it with rational coefficients, viewed as a QTT inverse module, where the structure of QTT inverse module is defined by saying that the multiplication by t is the action homology of the automorphism which goes from 1 copy to 0.1. And the Blanchfield form of the pair is a linking pairing defined on this infinite cyclic covering on the Alexander module with equivariant. So it's a pairing where we consider given two closed curves, we consider the linking of one curve with all the translated of the other one. And this provides an equivariant linking pairing, which is a polynomial. And this pairing, for any homology class, we obtain a rational fraction, which up to polynomial only depends on the homology class of the curve. Just say briefly. So why these two invariants are important here in this theory? Because the move of new Lagrangian preserving surgery preserves the Alexander module and the Blanchfield form. And more precisely, we also have the converse. So the isomorphism class of the pair AB, Alexander module Blanchfield form, characterizes the homeomorphism class of QSK pairs up to null Lagrangian preserving surgery. So this implies in particular that when we study our graded space G, we have a splitting of the graded space. So we can write G as the direct sum over all pairs, all other isomorphism class of pairs AB of the graded space reduced to QSK pairs with this Alexander module and Blanchfield form. And this is a graded splitting, in the sense that we have the splitting of each quotient Gn. So now, in order to study this graded space, we will fix a pair AB, an Alexander module and a Blanchfield form, and study the graded space GAB. Okay, so now we say we want to describe combinatorially this graded space. And the problem is that our move of null LP surgery is very large. So in order to give some combinatorial description, we need to reduce our move. So we define some elementary surgery, which are more specific moves. So the first one in genus 0 is just replacing a little ball B3 by a rational homology ball. So it's a genus 0 null Lagrangian preserving surgery. In genus 1, we have a move which is replacing a solid torus by a D torus. So a D torus is a rational homology torus, such that we have the boundary of our rational homology torus, TD, and on the boundary of TD we have two simple closed curves, alpha beta, whose homology classes generate the first homology group of the boundary of TD. And And we ask that the curve alpha, which generates the Lagrangian, has order D in homology in H1 of D. And we ask that the curve beta, its homology class is D times the homology class of some curve gamma in TD. And we don't want to have anything else in this homology group. So, first homology group of TD with integral coefficient is a direct sum of Z gamma and Z over dZ alpha. So this is just a specific rational homology torus. And the last elementary surgery, the most important one, is the Bourgogne surgeries, who appeared yet in definitions of the Garoufalidis theory and others. And this move can be defined in the following way. Take a Y graph, so a graph of this kind, and embed it in a manifold. In this manifold, you can consider a tabular neighborhood of your Y graph, or it's a genus 3 homology and genus 3 handle body. And inside this neighborhood, you insert this 6-component link. So we're taking into account some framing, and define the Bourgogne surgery along this Y graph as the usual surgery along this 6-component link. So this move has been introduced by Matveev, and in particular he proved that two closed oriented manifolds can be obtained from one another by such surgeries if and only if their first homology group and linking pairing are isomorphic. Okay, in particular, this explains why when you consider the Garoufalidis theory, you can reduce to integral homology spheres because it forms a class under such surgery.
Framings are all zero.
Yeah, you'll use the Blackboard framing. Okay, so with these elementary surgeries, indeed we can produce any Lagrangian preserving surgery. So that's what says this result. If you take two QHs A and B with a fixed LP identification of the boundaries, then they can be obtained from one another by a finite sequence of elementary surgeries and their inverses. And this is very important in order to describe the graded space GAB, because it implies easily that this graded space is indeed generated by all brackets defined only by elementary surgeries. So it's a step in the way to describe combinatorially this graded space. So now I want some diagram space describing this space G. So I'm looking for some diagram space depending on the pair AB and some surjective map onto GAB. So I now define the diagrams I will use. So we call AB colored diagram a unit trivalent graph with some conditions and labels. So first, the trivalent vertices are oriented, meaning that we have a cyclic order of the three edges meeting at the vertex. So in the pictures, I always consider this one. The edges are oriented and labeled with some Laurent polynomial with rational coefficients. The univalent vertices are labeled by elements of the Alexander module. And the pairs of univalent vertices, so here in the example we have only one pair, are labeled by some rational fraction with the condition that up to polynomial, this rational fraction gives the Blanchfield form between the two labels of the univalent vertices. So this gives a lot of conditions of this diagram. We will see in a moment what sense we can give to this label. So first I introduce a little generalization we call augmented AB color diagram. A diagram which is an AB color diagram with a finite number of isolated vertices labeled with prime integers. And we define the degree of such a diagram as a number of isolated and trivial vertices. Okay, now to define our space of diagram, we have a series of relations. So without the augmented, we have A and AB, which is a rational vector space generated by AB color diagram, up to all these relations. And we also define A and O, which is defined from augmented AB diagrams. So in these relations, we have the usual AS and IHX relations, which appear yet in Garoufalidis theory. We have some relations of linearity and edges, orientation reversal, holonomy, which appear yet in the theory of Garoufalidis and Kricker. And we have also formal relations which concern the univalent vertices. In particular, this relation of automorphism, which says that we can apply simultaneously on all univalent vertices, on the labels of these univalent vertices, an automorphism of the Alexander module, which preserves the blunt field form. And with all this data, we obtain a diagram space with a surjective canonical map onto the ready space G. So it's indeed the OG version which appears there. So I try to give an idea of how we define such a map. So we take some unit-round diagram with all the labels on it, and we embed it, we fix some perscective in K, and we embed our diagram in the complement of K. Now, on the edges, we have some polynomials. So, using the linearity on edges, we see that we only need to define our map on diagrams with powers of t on the edges. So now the idea is that when we embed our diagram, we have our knot, okay? And if we have some t to the k on the edge, we will ask that that the edge makes k terms around the knot. So this is for the label on the edge. Then, for any edge between two trivial vertices, we insert a little up link. Okay, so we are closer now to right graphs here. But on the univalent vertices, we need to put some leaves, some looped edges, and so we will put a leaf, say L, and we will ask that when we consider the lift of this leaf in the infinite cyclic covering, we consider the homology class of this leaf, and we want that this homology class is exactly the label of our univalent vertex. So this explains the data of this label on the univalent vertex. And now when we have a pair of univalent vertices, so we have some element gamma of the Alexander module there, some element eta there, and we said that we have some fixed rational fraction between those. So if we have v and v prime, we have some fv prime with a rational fraction, and the condition corresponding to this data if we have here a leaf L prime with the homology class of its leaf equal to eta, we ask that the equivariant thinking between L tilde and L tilde prime is exactly this FV prime. So this equivariant thinking is fixed up to polynomial by the data of the Blanche-Field form between gamma and eta, but the FVV prime fits exactly the equivariant thinking. So this is for all the data of this, on this diagram. We also have the univalent vertices. So the point is that once we have done all this, what we obtain in our in the complement of our knot is a family of Y graphs with or disjoint Y graphs, so intermanifold. So each of these Y graphs defines a Borromean surgery. And now, if we have an isolated vertex labeled with some prime integer p, we associate with it genus 0 surgery, BP replaced with B3, so B3 a little ball, and BP a rational homology ball, whose first homology group with integer coefficients is ZP. So from a diagram of degree n, so with n trivial or isolated vertices, we obtain the data of n disjoint surgeries in the complement of our knot. So this defines a bracket on the graded space, on the associated graded space, so an element of GNAB. So that's why we obtain such a map from this diagonal space to GN. So of course there are many things to check. Check that it does not depend on the embedding of the diagram. It does not depend on the chosen QSK pair. It respects all the relations and so on. But well, it works, and we obtain this canonical surjective and linear map from our diagram space to our graded space. So now we want to know if this map is an isomorphism. We have a complete description of our graded space. So first, for that we will reduce a little the question by considering the subspace of GNAB generated by the brackets defined only by Borromean surgeries. So we define it as a subspace of GNAB, meaning that we still quotient out by all the brackets defined by any surgeries. And when we consider this subspace, we obtain the same kind of canonical and surjective map, but with the space of diagram and AM. So we forget the isolated vertices in our diagrams. And it can be checked that if phi n b is injective, then phi n will also be. So we can consider only this map phi n b. Okay, so now we want to know that if this map is injective. And to try to do that, we will use the Lescop invariant. So the Lescop invariant is an invariant of QSK pairs defined from integrals in configuration spaces. And it takes values in another diagram space, which depends only on the annihilator of the Alexander module. So we have this diagram space, AN delta, which is, so for a given positive integer n, it's generated by delta colored diagrams. So I did not write a complete definition, but we have an example there. The delta colored diagram is a trivalent diagram whose trivalent vertices are still oriented, and the edges are oriented and labeled, but this time not only by polynomials, but also by rational fractions, with the condition that the denominator has to divide the annihilator of the Alexander module. So this defines a new diagram space, and
Excuse me.
yeah.
So t plus 2 plus t inverse can never be an Alexander polynomial.
Yeah, it can. Not for a knot in S3, but for a knot in any rational homology sphere, you can have any symmetric polynomial with rational coefficients. And it must not vanish at 1.
I see. Rational. Yes, thank you.
So, Christine Lescop proved formulas which give the behavior of her invariant with respect to neural LP surgeries, proving that her invariant induces a map on the graded space G. So here we consider the subspace GNB, and we have our map phi NB from the other diagram space to GNB, and we can consider the composed map psi n. So the idea is that if we can prove that this composed map psi n is injective, then this one will also be, of course. And so our question becomes, is psi n injective? Okay, so now the interest of this map psi n is that it's quite easy to describe in terms of diagrams. So if you take some unitary random graph, maybe this unitary random graph, its image by psi n, in this case psi 2, is given by the sum of all the possible closures of this diagram. So here we have 3 possibilities. Which has these 3 diagrams, and here we have all our labels. We have orientations and so on. And so for an edge between 2 trivial graphs, we have some polynomial that we keep on diagrams in the image. And when we close somewhere we glue 2 univalent vertices to close like that, and we have there 2 polynomials, Q, R, and we have between these 2 vertices the data of some rational fraction satisfying the rule with the labels of the univalent vertices. And what we will put on this edge here is QFR, with taking care of the orientations, but I don't give the technical details. So this, making this each time we glue 2 invariant vertices, we obtain a map from AN AB to AN delta, which is this map psi n. So it's quite easy to write, but not so easy to study. And so the problem is to know whether it's injective or not. In some cases, we have an answer. If the Alexander module is trivial, in this case it's very easy to study, because if the Alexander module is trivial, all univalent vertices are labeled by 0. And we have a relation, maybe I can, we have a relation of linearity on vertices, which says that indeed this diagram will be trivial, because we can put out the 0. So indeed, in the case of a trivial Alexander module, we do not have univalent vertices, so our 2 diagram spaces are the same. Because also in AN delta, if delta is 1, we have no denominators. So the 2 diagram spaces are the same, and psi n is just the identity. So in this case, we have isomorphism, and so we have a complete description of our graded space. So this generalizes a similar result of Garoufalidis and Kricker for knots in integral homology spheres with trivial Alexander module. So now a bit further, we consider an Alexander polynomial of degree 2. Since it has always an even degree, it's a polynomial case. And here we also just consider psi 2. So we look at the degree 2 diagrams. And here we can prove that psi 2 is injective. So we have injectivity here of psi 2 from A to AB to G to AB. So we have here an isomorphism, so typical description of this quotient of order 2. But we also see that this map is not surjective. So here we have A2 delta, and we do not have surjectivity here. So we see that our two diagram spaces here are really different. Okay, so this is a case where things work well, but bad news is that it does not always work. So now we consider an annihilator of degree 2, but an Alexander module which is the direct sum of two isomorphic copies, including the data of the Blanchard form. In this case, the map psi 2 is injective if and only if delta is different from t plus 1 plus t inverse. So we have one case where things do not work. Okay, so how do we prove this result? It's really pedestrian. The idea is that we compute the basis of the space A2 delta, and we compute the generating family of the space A2AB, and we check that this generating family is sent onto a free family. It's more complicated when you want to prove, in the case t plus 1 plus t inverse, that the map is not injective. Because in this case, you have to check directly that the generating family here is indeed the basis, that you have reduced at the most possible your generating family. And with the big set of relations that we've seen, it provides a very complicated computation. So for this result, we had to use a computer computation. Okay, so now a word on why does this does not work in this case, and why the map psi n is not always injective. In some sense, we could say that we would like to have indeed a map from a n delta to our graded space, to our quotients GMAB. Since our possibly universal invariant take values in this diagram space, this is the diagram space that we're interested in. So why do we not define this map from this diagram space? So of course, because we do not manage to do this. And we see that here we have a case where indeed it does not correspond. So the technical problem is the following one. When we take some trivalent diagram with the rational fractions on the edges, so maybe we have t, 1 plus 1 plus t inverse, and so on. If I want to define directly an element of G2AB from this diagram, what shall I do? We've seen that we embed the diagram in the complement of the knot, and when we have a polynomial on an edge, we can interpret this as terms around the knot. So we know that from Garoufalidis and Kricker. But when we have a rational fraction, we don't know what to do with it. So what we did with this diagram space gives part of the answer. I mean, in the sense that we can open our edge, put univalent vertices, and say we will choose elements in the Alexander module such that the Blanchard form between them is the class of this rational fraction. And so we can give sense to this label. And we can make the same with the other edge there, with two other elements of the Alexander module and so on. But the problem is that when we do that, we do not control the branch-field form between these vertices. And so we see that when we apply the map psi n, we will have not only our initial diagram, but two other that may be non-trivial. So the problem is that here we would like to put 0 as a rational fraction, but it's not always possible because it depends on the elements of the Alexander module that we have put there. But there is one case where we can do that. So if we fix an Alexander module A with branch-field form B, we can consider the Alexander module A prime, which is a direct sum of 3n copies of A, with a direct sum of the branch-field module, or of the branch-field form. When we do that, when we make this process, we can open one edge by choosing elements in the first copy of A. We open the second edge by choosing elements in the second copy of A, and so on. And in this case, we can choose to put zeros there as a FBV prime. And so this will work. So there are a few things to check. In particular, that AN AB is generated by such diagram on which the invariant vertices are only labeled by elements of the different copies of A, and 2 for each copy. But in this case, we indeed have that map psi n, so I call it psi n prime in this case, is an isomorphism, and we have a complete description of the quotient GMB for this value of n. Because we have 3n copies, we cannot put infinitely many copies. So we have a complete description of GNB or GKB for k lower than n, but not for upper n. So this gives a large set of cases where things work, but this implies to take big Alexander modules. We are interested in what happens with little Alexander modules. It has one of the more simple knots. But this also gives a way to rewrite our map psi n. So the idea is that we have here the diagram space for AB and the map psi n. Here's the diagram space for A prime and B prime, so 3n copies. And here we can define a map very simply by saying I take a diagram there, and for all the labels of the invariant vertices that are elements of A, I choose there to label them with the same element in the first copy of A in A prime. And so this defines, it's very easy to check that the map is well defined, and that it provides a commutative diagram. And since there we have an isomorphism, we have a rewriting of our map psi n. It's interesting to see it in this way, because here you have a map that sends a diagram on a linear combination of 2 to the n diagrams. Here you have a map that sends a diagram on one diagram. So this is more easy to study in this way. And so I'd like to finish with a rewriting of the problem, which uses, once again, this isomorphism in the case of 3n copies. So in this commutative diagram, we have first here the map as I described just before. So we take an AB colored diagram and we send it into the following diagram space with one more copy of A by deciding that the labels are understood in the k-1 first copies of A. Here we have our surjective map from the diagonal space to the graded space G. And here the maps induced by the Lescop invariant. And here we have to describe these maps. So from G and B k copies of A to G and B k plus 1 copies of A. So the idea is that we can fix some QSK pair M0 K0 whose Alexander module and first homology group is isomorphic to AB, and we can define a map by making the connected sum of QSK pairs with M0 K0. This defines a priori a map on F0 on this Alexander module, but it is to check that it induces a map on the quotient. And once we have this map between the quotients G and B, we obtain a commutative diagram, and the fact that at the level of three copies of the Alexander module we have isomorphism there, we have as a corollary that the maps they are induced by the Lescop invariant are all injective if and only if these maps given by the connected sum are all injective. This is a way to rewrite our question. And this is indeed what really interests us, because what does that mean? That this map is injective. If we have a look at our initial problem, so we have Lescop invariant there. And here we have AB. So the idea is that I said that the goal of this work is to give some universality property of the Lescop invariant and possibly also of the Kricker invariant. But in the case of the Kricker invariant, we have some formulas giving the behavior of the Kricker invariant with respect to Borromean surgeries, new Borromean surgeries, that they have to be extended to any Lagrangian preserving surgery. So we want to have universality properties of these invariants and to compare them. And the idea is that even if we don't have a complete combinatorial, very satisfying combinatorial description of the graded space, if we can prove that this map is injective, it precisely says that this is the universal invariant for finite type invariant of QSK pairs up to degree 0 and 1 invariants that are known. So this is the real question, and this really rewrites our question. So I'll stop there. I thank you for your attention.
Any questions or comments?
Do you have geometric application here? Geometric application.
Geometry?
Geometric application.
No.
Application?
So even for small degrees, such universal invariant is not constructed yet, or
Is not
for small degree.
personal degree.
If n is 3 or something, still it's difficult.
We've seen that we have a counterexample in degree 2 there for this case.
Yes.
In degree 0, we just have the isomology of logic form, and in degree 1, the cardinality of the first homology rule, and so can begin to improve.
Any questions? Let's ask the